At the University of Washington, a team of LSST scientists are writing the software to identify and track any objects in the sky that change with time. They are working to build the largest census of our solar system ever undertaken, and, with groups like the B612 Foundation, to see if any of these asteroids might one day pose a threat to the Earth.
So there's two true things about humanity throughout the ages. One, we're explorers. We love to go and find out the unknown. And two, we've always looked up at the sky and said, what's up there? LSST is designed to help us answer both of these things and connect us in this long tradition humanity has had. We're going out into the solar system and making maps to find out more about where our solar system came from and where it's headed.
The LSST truly is the next step in exploration and mapping of the solar system. This telescope will create the largest census of asteroids out there. By the time LSST is done, we will have quintupled the number of known asteroids. We will have increased the number of precise measurements by at least a factor of 10, and we will have discovered about 3/4 of large asteroids that may collide with Earth. But what's interesting to me as well is what it takes to do all of that. The 21st century astronomy will be driven by big experiments, by big data, and above all, by very, very clever software. With LSST, we've already reached a point where too much data is being collected for a human to even glance at each image, let alone to have a human identify objects and manually perform measurements. So for LSST, or for astronomy really, to thrive in this century, we need to teach computers how to do all that we used to do ourselves. Teach them how to look at astronomical images, teach them how to find objects, teach them how to measure objects, how to understand them, and ultimately how to alert us when there's something really special and interesting that's popping up. And that means writing software. So this is what we're doing for LSST, and this is why working on it sometimes feels like being in a tech startup. We have teams building supercomputers, we have teams developing databases, we have teams developing image processing codes. And here at the University of Washington, we even have a team developing code that will use LSST data to map out the solar system, to find asteroids, and also, more broadly, enable all of time domain science.
So when we say time domain science, what we mean is tracking things that change over time. So, it looks different one night and then we take a picture later and we're like, oh my gosh, something changed. And asteroids are like the perfect example of this. My background is actually a little more in stars, so it's cool also to see things might get like fainter or dimmer if it's a star. But if you have an asteroid, it might get fainter and dimmer, but more importantly, it's going to appear to move from one image to the next. And so when we say that LSST is going to be great at time domain science, what we mean is that we're repeatedly revisiting the same areas of the sky over and over again, and we'll be able to tell if there's an object moving through that part of the sky. And since asteroids orbit the sun, they're a lot closer to us than distant stars or faraway galaxies. We can actually see their motion on a human timescale, an order of days, weeks, months, even years. We can track how they're moving around the sun.
How do we find asteroids? Here's a fun analogy. Imagine taking two pictures of traffic on your street, maybe 1 second apart. In the first picture, you see there's a car directly in front of your house. In the second picture, you see that car has moved. Now it's 10 feet to your left. So what does that tell you? Those two observations tell you that the car is moving. They tell you it's going from right to left, and also tell you how fast it's moving. So you can do an analogous thing with asteroids. You observe the sky, you observe every region twice, and you take a look at all the star-like objects in there that are moving. But coming back to the car, you see that car and now you know it's moving from right to left. But what that doesn't tell you is where it's going. It doesn't tell you whether it's going to the supermarket down the street, or to a different neighborhood, or where it's leaving town entirely. Now, to learn that, you need much more observations. You need many more observations, and you need them over longer time spans. Exactly the same thing happens with asteroids as well. Based on two images, you can tell that an asteroid is there, but you can't tell where it's going. You can't tell its orbit. For that, you need a lot more data. So imagine if instead of taking a photo of the car with my cell phone, you take satellite photos of the street. So what you can do then is look for that car in each and every image that you've taken. And when you find the car, you connect the individual observations to discover where it's going. You may discover it regularly commutes, say, to a neighboring town. What that tells you is a pattern of its motion. You know its orbit. You know its trajectory. So the same thing works for asteroids. If we reobserve them multiple times over many nights, we can deduce how they travel through the solar system, where their travels take them. We can deduce their orbits. There are millions and millions of asteroids in the solar system. With LSST, we will collect several billion observations of those asteroids. Each night, we will observe about 1 million or so of them. And all these asteroids move, and they look incredibly alike. So telling that this asteroid I observed on Thursday is the same as the one I observed on Monday, to link those two sightings, becomes phenomenally difficult. So the only way to solve this, really, is by trying out virtually all the combinations that are plausible. And we do that by constructing clever algorithms to perform this, what we call linking, and building big supercomputers to run those algorithms.
Another particularly amazing thing about LSST from the standpoint of our group here at the University of Washington is the software involved in analyzing the data. Our group is working on what we call the alerts processing stream. So this takes the data that comes off of the telescope and analyzes it, calibrates it, finds all of the things in it that changed from the previous time we looked at that spot on the sky, and we're done with that before the next exposure comes off the camera. We have to be fast if we want to be able to find things before they've moved too far or before they've changed too much, so that we can tell other telescopes to follow up and help us nail down orbits of asteroids and find out more about their properties.
So the software I'm writing here in the data management team with the alert production pipeline group at University of Washington is specifically for that real-time processing. You know, how are we going to detect if something real in the image changed versus just, oh, it was cloudy and then the clouds went away, or oh, there was like a pixel that was being cranky and then it was fine in the next image. You know, what's the actual astrophysical object, you know, the star, the galaxy, the asteroid, the whatever, that changed in the image? And can we maybe even give a vague classification of what kind of thing it is, but at the very least, can we say for sure this is an actual real change in brightness or in location, and then send that information out to the community as a whole so they can do science with it.
So finding a lot of asteroids is important for many reasons. The first is you want to identify as many asteroids as possible that could potentially one day impact the Earth. The second reason is you also want to make sure that you've identified targets which might be interesting to maybe visit one day. And lastly, every single asteroid that you discover can potentially one day become a data point in a simulation where you want to try to model the formation of our solar system. In terms of finding more asteroids, the more the better.
Asteroids help us understand the formation of the solar system when we study the distribution of their orbits and their physical characteristics. This video by Alex Parker shows us the currently known asteroids. Each point is a real asteroid, and the colors of the asteroid in the video change as you get further from the sun because their actual colors that you see change as well. Asteroids closer to the sun tend to be more stony and dry, while asteroids further from the sun are more carbonaceous and water-rich. And these changes in their physical composition are reflected in the colors that we see and will observe with LSST. When we look at the largest, brightest asteroids, the earliest asteroids to be discovered, this trend with distance from the sun is very strong, so it influenced our understanding of how planets formed, making it look very orderly. Planets formed in their current location and were formed from the materials present at that location in the solar nebula. But when we started to find smaller, fainter asteroids, we start to see that not all of the asteroids follow that trend. This, plus other evidence from the outer parts of the solar system, has made us take another look at planet formation. Newer models of the history of our solar system reveal a much more chaotic process, with Jupiter flinging small planetesimals all over the solar system and Neptune forming much closer to the Sun but moving outwards to its current position. With LSST, you will find many smaller asteroids and measure the orbits and colors, which will help us understand these models of planet formation and the history of our solar system in much more detail.
So LST will definitely have an easier time discovering the bigger asteroids. And part of our data output will be the means to calculate or to at least predict what kind of asteroid that might be. So either stony iron, or some other type of asteroid. What LSST will definitely be able to do is identify interesting asteroid targets, whether that's for maybe a redirect mission where we put an asteroid into orbit, or maybe a mission where we want to visit an asteroid and potentially mine it. These are all very much within the grasp of LSST.
In 2013, a small asteroid came and hit the Earth near the Russian town of Chelyabinsk. Now, fortunately, it came in at a very shallow angle. It came in only about 18 degrees off the horizon. And as a result, when it hit the atmosphere, a little bit like skipping a stone on a pond, it stayed up in the atmosphere. But it had a power of several hundred times the Hiroshima nuclear bomb. It broke 1 million windows, it sent like 1,000 people to the hospital for various injuries. If that had come in at a much steeper angle, it could have killed 1 million people. In 1908, there was another impact. This happened in a place called Tunguska in Russian Siberia. And it devastated somewhere between 250 and 500 square miles. Total destruction. Now, at the time, the only people that were there were some migratory reindeer herders. And so, and also in 1908, Russia was in the middle of going through a series of revolutions that would create the USSR. And as a result, it was never properly studied. If Tunguska had hit just a couple hours different time, plus or minus, it would have hit in North America or Europe or the populated parts of Asia. And if that had happened, it would have been an enormously traumatic event. It could have killed millions of people, and even if it didn't kill them, the devastation would have been shocking. So if you imagine an alternate universe where Tunguska hit in a more important place, the whole 20th century would have been about, oh my God, we have this risk from the skies. Instead, as luck would have it, Tunguska hit in the most ignorable spot on Earth. In fact, I argue if it actually hit the Atlantic or Pacific Oceans, we would have known a lot more about it. It would have destroyed a bunch of ships at sea, there would have been a bit of a tsunami, a whole lot of things would have drawn our attention. Instead, it hit in the most ignorable spot on Earth. We can't afford to have these things sneak up on us like that. And with LSST, there's an excellent chance that we will map asteroids that could hit Earth.
The most important aspect of LSST in this context will be to provide much longer early warning times in case we discover a potentially hazardous object. In case we think there might be an impact, we would know about it much earlier using LSST data than the assets we have today. As Don Yeomans, NASA asteroid scientist, said once, for asteroid mitigation, there are 3 important ingredients. We have to find them early, we have to find them early, and we have to find them early. And LSST will excel in that. Why is it so important to find them so early? There are 2 different sets of reasons. There are 2 different things we can do in case we find a potentially dangerous asteroid, potentially hazardous asteroid. We could take flight or we could fight. In case of fighting, we have basically 2 options. As we predict that asteroid on its orbit will strike Earth, we could, if we discover it early enough, we could change its orbit by, for example, gravity tractor, which is a spacecraft that exerts gravity on asteroid. Change it slightly. If you do it early, it's not that much, and then it will miss Earth when it was supposed to strike. Or the other option is to send some spacecraft with nuclear explosives and break it into small pieces, and when these small pieces come to Earth's atmosphere, they will burn in the atmosphere, and those small ones will not be nearly as dangerous as a whole big single piece asteroid. The other option, which is much more probable, is that we'll have to take flight, that it's too late to change the orbit of the asteroid, that basically we'll discover it on its last descent to Earth. And that will probably happen with smaller objects, say 100 yards
because these small objects are much more numerous than big ones, and therefore probability of discovering small one is much higher than for the big ones. So the most likely scenario is that we'll realize, oh, there is an object on its last descent to Earth, it will strike city X or country Y. What can we do about it? Well, there isn't much you can do except to minimize damage to property and population. So you have to move population as fast as you can, and this is where early warning times are very important. So what we can do today on timescales of few days, warning times of few days, with LSST they will be weeks. And for those orbits and objects where today we can see them few weeks in advance, with LSST we would have few months in order to organize ourselves to do something like FEMA effort to mitigate impact by moving population. This is where LSST could make a big difference to lives and to property.
I think my one takeaway for asteroids in general, or science with LSST, is that we today have a good knowledge of the questions we might want to be asking. We know kind of what we want to look for, but the thing about a data-rich environment and the sheer volume of data that LSST will create is that there are going to be answers to questions we don't even know how to ask today. And that's really the richness of having such a data-intensive project like LSST. And in the context of asteroids, that will lead to science and discoveries which we can't even fathom today.
The LSST is probably the most exciting project in astronomy that I could be a part of right now. And to me, it's one of the coolest projects across the board in all of science. One of the reasons that LSST is so interesting and really transformative is that it's much more than a telescope. It's much more than astronomy. It's a data project.
What's exciting about LSST is that it'll produce more data of this type than has been available before, at a higher quality than has been made before, and the tools being developed will be more powerful in many ways than tools previously, and that combination will create a huge increase in the amount of science that's able to be done from this project.
So one of the most exciting things that I find about LSST is the way that it will enable many people to participate in the sciences. So LSST is designed to do detections on a single night and send out alerts. So fast-moving objects coming near to the Earth will be detected, and we can put alerts out so that many people can view these, transient objects, which would otherwise be difficult to detect.
With all of these telescopes and surveys coming online, surveying the sky with unprecedented depth and resolution, we have an incredible opportunity for new discoveries about our solar system, the Milky Way in which it resides, and even the universe as a whole. The challenge we face for the next decade is not about how we collect or process or even store these data. We have a good idea how to do that. The challenge we face from these new telescopes is how do we make sense of the data? How do we extract the knowledge from all of these streams of information? Knowledge that will provide us the clues for how our solar system formed. As an asteroid moves across the sky, tracing its path is like playing a game of connect the dots. But at the scale of the data from telescopes such as the LSST, we're playing not just one game of connect the dots, but a million. And where all of these games are superimposed on top of one another. And this is hard. It requires new ways of thinking about data. But if we can do this, maybe we can understand the processes that gave rise to our solar system. Maybe we can detect planets beyond the orbit of Neptune, or identify and deflect the asteroids that might otherwise impact the Earth. To answer these questions, we need to bring together astronomers and computer scientists, statisticians, and citizen scientists as a whole, each bringing a unique contribution to our search for the origins of the solar system. Centers such as the Dirac Institute are developing the tools and the techniques, the algorithms and the methodologies for searching through trillions of measurements to find the subtle features that will lead to these new discoveries. In fact, our ability to make scientific breakthroughs over the next decade will be governed by our capacity to deal with the scale and the complexity of the data. The scale and the complexity of data from a new generation of telescopes and experiments that will enable us to explore the inner and the outer reaches of our universe.